explanation.
Good afternoon. I am Manmohan Pandey. I am teaching this course on two-phase flow with phase change in conventional and miniature channels. And we have a live session today. So far, none of the participants have joined the live session. Maybe sometime later they will join. So if there are any queries, they can ask. So before that, I will make a presentation. I will summarize the course, and then you can ask if you have any queries. So those who have joined in Microsoft Teams, those who are going to join, they can unmute themselves and ask questions orally, or I think they can type in the chat box also. And in those who are going to join in YouTube, they can ask questions through the chat. So now let me share the slides. Slide I have shared, but in YouTube it is not showing. To put it in the slideshow mode, I think. Okay, now it is showing. Okay, so the course title is Two-Phase Flow with Phase Change in Conventional and Miniature Channels. In this course, as you know, we have discussed two-phase flow, that is gas and liquid flow, not the other types of two-phase flow, gas and liquid flow, mixture of gas and liquid, and with phase change, that is phase change can occur from liquid to gas or gas to liquid. I am Manmohan Pandey from the Department of Mechanical Engineering, IIT Guwahati. So now I'll summarize the salient points of the course. In two-phase flow, there are many flow regimes. Unlike single-phase flow, a single-phase liquid flow or single-phase gas flow, there are only two major regimes, laminar flow and turbulent flow, and in between there is transition. But it's in slideshow mode, but in YouTube it is not showing a slideshow full screen. It is not showing. It is showing like this. This is in slideshow mode. So should I continue like this? In Teams, how is it showing in Teams? Is it showing full screen? Okay, I'll unshare and share again. After making full screen, I'll share it again. Oh, I have unshared, but still it is showing in YouTube. Now I cannot open this. Or should I share the whole screen? I'll share the screen itself. Okay. Still in YouTube, it is not showing. Okay, and now it is showing full screen. Okay, thank you. Okay, so in two-phase flow, there are many flow regimes, unlike single-phase flow, in which there are only two major regimes, laminar flow and turbulent flow, and in between transition. So two-phase flow is much more complicated compared to single-phase flow. And these flow regimes depend on many factors. Whereas in single-phase flow, there is only one non-dimensional parameter, laminar Reynolds number, which characterizes the flow regime. In two-phase flow, there are many factors. It depends on the orientation, whether the flow is vertical or horizontal flow. There are different flow regimes, where some of them occur in vertical flow only, some in horizontal flow only, some in both. Okay. And I was seeing the YouTube chat, and nobody is there. Then it will depend on adiabatic or non-adiabatic, whether the flow is adiabatic or whether it is a flow with heat transfer. Some flow regimes occur only in non-adiabatic flow, but not in adiabatic flow. Then it will also depend on whether the liquid flow rate is low or high, especially in horizontal flow. If the liquid flow rate is low, we observe certain flow regimes. If it is high, we observe certain other flow regimes. It depends on whether the gas flow rate is low or high. As the gas flow rate increases from a low value to a high value, we see a series of flow regimes. There are flow regime maps to determine which flow regime will occur, to predict the flow regime. In single phase flow, we have only Reynolds number, and we check the value of Reynolds number and predict the flow regime. But in two-phase flow, there are many parameters. So there are flow regime maps to predict the flow regime. There are many flow regime maps for vertical flow and horizontal flow and different types of flow arrangements, different types of geometries. In this course, we have discussed only two flow regime maps, one for vertical flow, which is by Hewitt and Roberts, and another flow regime map by horizontal flow by Baker. So in both of these flow regime maps, we calculate two parameters, and then based on the values of those two parameters, we locate the point on the map. And then based on the location of the point, we predict which flow regime is most likely to occur. Then in the course, we have discussed modeling of two-phase flow. The modeling of two-phase flow can be done based on the flow regime, and there are some models which are not based on the flow regime. If we know the flow regime, then we can use a flow regime-based model. And if we don't know the flow regime, then we have to use the model which is not dependent on any particular flow regime. So in this course, we have discussed only those models which are not dependent on the flow regime. And we have discussed three models: homogeneous equilibrium mixture model or HEM model, separated flow model, and drift flux model. In the homogeneous equilibrium mixture model, it is assumed that the two-phase mixture is a hypothetical fluid, and it has some hypothetical properties which are obtained by weighted averaging of the properties of the two phases, gas and liquid phases. It is assumed that both phases move with the same velocity, equal velocity. Actually, there may be a difference in the velocities. And thermal equilibrium is also assumed. That means both phases are at the same temperature. So if it is a liquid and vapor mixture of the same substance, then they have to be at the saturation temperature at the local pressure. Both phases have to be at the saturation temperature. So temperature is a function of pressure. In the separated flow model, separate motion of the two phases is accounted for. So the two phases can move with different velocities, and it is considered in this model. And thermal equilibrium is assumed in this model also. So we write separate balance equations, mass balance, momentum balance, energy balance for both phases. and the interaction between the two phases is also accounted for. Mass exchange, momentum exchange, and energy exchange between the two phases, and also the interaction with the both phases with the ball. There is another model which is more elaborate than the separated flow model, in which thermal equilibrium is not assumed. So the two phases can be at thermal non-equilibrium, but that is outside the scope of this course, so we have not discussed it. Then there is a drift flux model, which gives us the best of both. It has the simplicity of the homogeneous model, in which we don't have to write separate balance equations for both phases. And it also accounts for the relative motion between the phases using empirical correlations. Okay. In the homogeneous model, we write the balance equations for the mixture. And the momentum balance is transformed in such a way that it is every term is a pressure gradient. That is rate of change of pressure with the axial coordinate Z. This is one-dimensional steady-state model that we are discussing. In this course, we have restricted to one-dimensional steady-state model only with constant cross-sectional area. So the momentum balance, after doing the necessary mathematical operations, we get it in this form. The pressure gradient, negative of the pressure gradient, because usually the pressure decreases as we go downstream along the channel. So that is why we write in terms of the negative of the pressure gradient. So the total negative pressure gradient is equal to the pressure gradient due to friction, pressure gradient due to acceleration, and pressure gradient due to gravity. The sum of these two. I think I should use the laser pointer. Laser pointer? It is not there. Okay, anyway, I'm using this, the cursor. Laser pointer is not there, I think. Huh? Oh, this one. Hmm? Hmm? Oh. Okay, okay. Pointer. Where is it?
Choose a color. Mark.
Where is the pointer? Mark? No, I don't want to mark. I just want to show. I think it is not there. No, no. It is not there. Anyway, I don't want to write. Okay, I'll continue with this. And how to switch on the camera? Escape. Okay. Okay, so the momentum balance is as follows. The total pressure gradient is the sum of the frictional pressure gradient, acceleration pressure gradient, and gravitational pressure gradient. Okay. And then the acceleration pressure gradient is written in terms of the mass flux and the specific volume. And then after some algebra, we get this expression that pressure gradient is equal to 1 upon 1 minus m square, and in the bracket we have 2f by d g square v bar plus g square vfg dx by dz plus g sin theta upon v bar. So in the bracket, the first term comes from the frictional effect, the second term comes from the acceleration effect, and the third term comes from the gravitational effect. And here m square represents the compressibility of the vapor phase or the gas phase, and it is given by minus g square x dvg by dp. dvg by dp is negative, so we can write it as g square x absolute value of dvg by dp. And dvg by dp is a property. It is the rate of change of one property with respect to another property. So it is a property, and depending on the pressure and the mass flux and the quality, the value of m square may or may not be negligible compared to 1. So if the value of m square is much less than 1, then we can neglect it, and 1 minus m square is taken as 1 approximately. And then we don't have this 1 minus m square, and we have only this expression which is in the square brackets. So we get this pressure gradient is equal to 2f by d g square v bar plus g square vfg dx by dz plus g sin theta upon v bar. And then to obtain the pressure drop, we have to integrate this over z from the inlet to the outlet. So with some assumptions, m square has been neglected already, and with some further assumptions, this expression can be integrated analytically, and we can get an expression. So we have got an expression for the pressure drop for both for different types of cases, for a uniformly heated tube and an adiabatic tube and uniformly cooled condenser tube also. Okay, this m square parameter represents the compressibility of the vapor phase, and if m square is very small, we can neglect it. And the other extreme is that when m square approaches 1, then 1 minus m square approaches 0, and then the pressure gradient approaches infinity. So that is called choke flow, and that much flow, that is the limit of the flow through that channel. More than that just cannot flow through that channel. In fact, flow equal to that also is not possible through that channel. So to get that maximum limit, we set m square equal to 1, and then from that we get the maximum mass flux, expression for maximum mass flux, and expression for the maximum mass flow rate. Now the separated flow model, the mass and momentum balances for the two phases are written separately, and then from that we get the expression for the total pressure gradient. So again, it has the same format. The total pressure gradient is the sum of the frictional, acceleration, and gravitational pressure gradient. But these expressions are complicated and longer compared to the homogeneous model. So we get expressions for each of the pressure gradients. And since these expressions are complicated, to evaluate them, we use graphs or correlations. And there is a quantity called two-phase frictional multiplier. In fact, 4 such multipliers are defined, which we will see in the next slide. And there are graphs and correlations for the white fraction. So there are different correlations given by different researchers, and some researchers have given their correlations, empirical correlations. Some researchers have given in the form of graphs, and some have given in the form of correlations, that is algebraic expressions. 4 frictional multipliers are defined. So this dp by dz subscript capital F is the frictional pressure gradient. And on the right hand side, we have subscript capital F, comma FO. This is the hypothetical pressure gradient that would have occurred if the entire fluid were in liquid phase. And then we have here in the second line, we have capital F, comma small f suffix. So this pressure gradient is the hypothetical pressure gradient that would have occurred if only liquid were flowing through the channel. Okay. So the corresponding two-phase multipliers are denoted by phi FO square and phi F square. And then in terms of the mass flux and quality and the friction factor, we have this expression 2FFO by d g square Vf by FO square. And here we have 2FF by d g square 1 x whole square Vf by F square. Now similarly for the gas, two pressure gradients are defined, two hypothetical pressure gradients, subscript F, GO and subscript F, G. This is similar to those for the liquid. Two frictional multipliers are defined, phi GO square and phi G square. And in terms of the mass flux, quality and friction factor, we have these two expressions. There is another important parameter which is defined as the ratio of the hypothetical frictional pressure gradient, assuming that only liquid were flowing through the channel, upon in the denominator there is the hypothetical pressure gradient assuming that only gas is flowing through the channel. So in terms of frictional multipliers, it can be shown that this is equal to phi F square upon phi G square. And four flow regimes are defined based on the whether the two phases are laminar or turbulent. So there is turbulent regime in which both phases are turbulent, and the corresponding Martinelli parameter is denoted by capital X subscript TT. And then there is viscous turbulent regime in which liquid is viscous or laminar and gas is turbulent, and it is denoted by XVT. And then turbulent viscous regime in which liquid is turbulent and gas is laminar, and it is denoted by XTV. And then there is viscous regime in which both phases are laminar, and it is denoted by XVV. So we can derive the expressions for these two these regimes. We can easily derive the expressions because for these two regimes, X, the Martinelli parameter, turns out to be independent of the mass flux and the channel diameter. So we have an expression for XTT. This is based on the Blasius correlation for the friction factor for turbulent flow through smooth pipes. It is Vf by Vg whole raised to 0.5, mu F by mu G whole raised to 0.125, and 1 minus X upon X whole raised to 0.875. For XVB, we use the friction factor as 16 by Re, the laminar friction factor based on the exact solution of Navier-Stokes equations. So we get Vf by Vg raised to 0.5, mu F by mu G raised to 0.5, 1 minus X upon X raised to 0.5. Now the drift flux model. The drift flux is the volumetric flux of the gas phase with respect to the hypothetical plane, which is moving with the velocity J. J is the total superficial velocity or the total volumetric flux, and it is equal to the a weighted average velocity of the two-phase mixture. So JGF, the gas drift flux is equal to alpha into ug minus j. This is the relative velocity of the gas with respect to the plane moving with velocity j, and jfg is the liquid drift flux. It is defined in a similar way, and it is equal to 1 minus alpha into uf minus j. And jgf is equal to minus jfg. Now, jg is expressed in terms of alpha, j, and vgj, and then we take the average, area averaging, and then we define two coefficients, C0 and VGJ. So then it is written, Jg is written in terms of these quantities. It is Jg is equal to C0 average alpha into average J plus VGJ into average alpha. Here C0 is called the two-phase distribution coefficient or concentration coefficient, and it represents the overall slip over the cross section, because the concentration profile or the void fraction profile is not similar to the velocity profile usually. So the average of alpha and j, average of the product of alpha and j over the cross section is not equal to the product of the averages of alpha and j usually. So therefore C0 is usually not equal to 1, and it is determined empirically using empirical correlations. Then VGJ is called the gas drift velocity, and it represents local slip. VGJ is defined as the alpha into UG minus J, the relative velocity of the gas phase with respect to J, multiplied. These two quantities are multiplied, and then the average is taken over the cross section. And in the denominator, we have average alpha. Here we have the local relative velocity UG minus J. So therefore, this coefficient represents the local slip at each and every point over the cross section. So then finally, we revert to the one-dimensional model, and we can write in terms of the one-dimensional quantities, alpha is equal to Jg upon C0j plus Vgj. So using this expression, we can determine alpha, and for that we have to determine C0 and Vgj, and these two parameters are determined using empirical correlations. Okay, so there are several empirical correlations for C0 and VGJ. In the course, some empirical correlations are given, and numerical examples have been solved in the course for all the three models: homogeneous model, separated flow model, and drift flux model. In the separated flow model, we have considered Lockhart-Martinelli correlation and Martinelli and Nelson correlation, and we have solved problems for determining the pressure gradient at a point and for determining the pressure drop over the channel. For all these models, we have solved in the course. So that is the summary of the course. Now, if there are any questions, then I'll answer. So in Teams, I don't find any of the participants. In YouTube also, no participant is there. And in the chat also, there are no questions. So I hope this YouTube will be available later also, and they can ask queries. If they have queries, they can ask in YouTube. I don't know. I'll check in YouTube, and if there are any queries later on also, I'll answer them. Okay. So then we can close the meeting. stop the sharing. I'll stop sharing the slide. Okay. And now should I close the meeting? Leave the meeting.